and it's going to be about introduction to address spaces. Okay. Good. So till now, we were talking about process abstraction and how the uh, OS makes every process think that it has the CPU to itself, and how does the time sharing of the CPU with different processes. And we saw what, like, mechanisms were involved, what were the policies, the scheduling policies, and so on. So now we'll move our attention to the next module, which is going to be about memory, that how the operating system manages memory, and what are the abstractions, and like what are the mechanisms involved, what are the policies involved, and so on. Okay, so first thing is going to be okay. So why this was needed? Okay, so what was there in earlier systems? So if you look at yeah, so if you look at earlier machines, then what used to happen was there was no abstraction as such. So what used to happen, like, so suppose this was all the memory, and then the OS used to sit in the top part, and here the current process would sit. Okay. So suppose, the OS started at 0, and then whatever 128, let's say KB, at that location, the current process started. So that was it. Like at one time, just one process would be there in the memory. So there was no abstraction. And even the OS was, as we had seen earlier, just a set of routines. Okay. And like, which is just basically a library. It did not perform any, like, administrative tasks. And the point was that at one time, only one process would reside in the physical memory. Okay. And this was fine because in the earlier machine, there was no expectation from the user side. The user would do all the, like, hard work. The IO was not that complicated. So this was like a very simple system where just the OS would be there, which would be just a bunch of functions or libraries. It was just library. It would just give some routines for the programs, and then you load your program into the memory. And at one time, only one program will be there, and then that program would run. And then when you want another program, then you would switch it, right? Okay, good. So then came the era of multi-programming and time sharing. Okay. So what is multiprogramming? Multiprogramming is running multiple processes which are ready to run at any time. Okay. And also we might have multiple users for one computer, right? And they might time share. Yeah, good. So now what was needed in that context when multiprogramming and these time sharing things started was that one that you could efficiently do the job, effectively utilize the CPU, and the other was interactivity. That is, different users should not be wait for a long time, right? So these were the goals which were there. And then, so what is one very basic approach to do this? That okay, so now we need to provide time sharing. So we have to run like many processes. We want to cater to many users. So how can we do that? So one basic, like very naive approach can be that okay, run one process for a short while and then like swap it with another. So give it full access to memory, and then when we need to run another process, first stop the current process and then save all the data that is there. And where do you save the data? To disk, because you want to load another process to the memory, right? And then run it. So this is, as I said, a very naive way of doing multiprocessing or time sharing. And what is the problem with this? Anyone?
Disk access is take a very long time.
Exactly. It's too slow. Why? Because, as you said, access takes long time. And especially when the memory grows of a process, then you need to copy like large chunks of memory to the disk. Good. And yeah, so disk access takes longer time, as compared to like saving to the registers, saving register to the memory is fast. But saving an entire memory to disk, this is super slow. Good. So this is the problem with this basic approach, that this is like basically too slow because it will involve the disk, and copying large chunks of data from memory to disk is going to be too slow. So what would we want to do? At least like what would be the first thing? First thing is going to be that we want to keep many processes in the memory. Okay. So allow processes to remain in memory while we switch to another process. Okay. And this will make time sharing will be efficient. Good. So like, for example, what we would want it to look like this. That the memory is divided into like multiple parts. The OS sits here. Maybe some process A sits here. Then again, process B sits here. Is there a question? Suppose this part is free. Nothing is here for now. Then again, let's say these parts are free. And process C sits here. And then again, this is free. Okay. And yeah, so there are some, let's say, designated places where this is. So let's say we make blocks of 64 KB for now, and so on. Good. So what this diagram represents is that first, each process has a small part of physical memory. Okay. And while one runs, others can sit in the ready queue. Okay, good. So this is what we want to achieve. Now, what can be the issues with this? What is the major issue?
That if we give one process some unrestricted access, it could corrupt other processes memory.
Exactly. So that's going to be protection. And as you said, we don't want a program to access or override another process's memory right? Or even like so, or the OS also, that it should not be able to write something on top of the OS also, right? So for this purpose, the OS creates this abstraction called the address space. Okay, so this is created by OS and easy to use abstraction. Okay, and like how do we like sort of, not exactly a definition, but what is an address space? It's a running program's view of the memory, right? So actually the memory looks like this in the system, but what a program will see will be different, and that's what we call its address space. Okay. Okay. So what does an address space contain? So basically it contains all the memory, uh, like mm, basically everything about the program when it's running. Okay. So all so we had encountered this term called memory state in the first chapter, I think. That okay, what is the memory state of a program? It is basically everything about the program. And what did it have? There were three major components. The first was the code, which is the instructions of the program. Second, we had seen was the stack. This was to like or for local variables, storing the local value variables. Passing parameters, return values of functions. And basically it helps to know where in the or where is the program in the function chain. So you're calling many functions, then like it will keep like piling up on top of the stack. So for every function, you grow the stack. Okay, and the third one was heap, and we had seen earlier that this is for dynamically allocating. Okay, and this is like by the user. So this will be managed also by the user. Okay. So there are other things also like some static data, etc. We'll ignore them for now, and we'll talk about these three components. Okay, good. So how does now how does the process now use the memory? Is the question, right? Any question till now? So, no. Okay. So how does the the address space of the process looks like? So let's say it starts at like 0 KB, it like finishes, let's say, at 16 KB. So below is the stack. Above is the code. Let's say this is 1 KB. And here is the heap. So this is 2 KB. And this space is free. Okay. So, and now the question can be that why we put the heap at the top and stack at the bottom. And the answer will be, any guesses?
So that they can expand into the same space.
Yeah. So that they can expand or grow. Okay. So here, like we saw, heap starts right after the code. Okay. So at 1 KB in this example for right? And the stack starts at the end of the memory at 16 KB. So the heap, of course, goes in the positive side. The heap grows downwards and the stack grows upward. So the heap will expand in this direction, the stack will expand in this direction. and this space is free, so they grow to take up this space. Okay, but just to keep in mind that this arrangement is just a convention, and you can arrange it like if you are designing an operating system, whichever way you think will work the best. And in fact, like in some places you need to arrange it in a different way, and things might not look so pretty that okay, there is a heap stack and they are just growing in the free space. Like suppose you have multiple threads in the same memory block, then how do you manage that? So then things will not look that pretty. So just to point out that this is just a convention, and this can be done otherwise, but like generally it is used this way. Okay. So what is this diagram though? So we have seen these two diagrams. One was this, and one is this. So how are they fundamentally different? So yeah, you can answer. What is the main difference between these two diagrams, even though they represent memory?
So this diagram
And the previous one, which was this, is the other diagram just a like okay? Let me narrow down the question. Is the other diagram just a like zoomed in view of this one?
yes, sir.
No, so actually not. So that is the main thing that the abstraction is. So this diagram is just, I mean, you can say that it is a zoomed in view in a very rough sense, but that is not actually true. So you should not think of it as a zoomed in view of the earlier diagram, because that's not what it is. So this diagram is just this diagram, let's say figure 2, is just an abstraction that the OS provides to the program. Okay, so of course the program does not really sit in physical memory from, let's say, 0 to 16 KB as it is shown in this. It can be located at some arbitrary address. Okay, so why I'm like differentiating, because this picture does not actually represent how the physical memory looks like. This is just the program's view of how its memory looks like. So this distinction is quite important, because when like even though it might happen that initially it looks like uh, the a zoomed in version of the previous one, which I don't think it does, but again we don't know what the OS is doing there. And but when a program grows and the memory grows, then the program's view will still be exactly the same. It is not going to change. The program's view is going to be code, heap, and stack, and it will grow the stack, it will grow the heap. This is not going to change. It's not that now, somewhere else, some other stack will come and so on. So this is all the memory that the program can have. So yeah, a program cannot use up all its memory and then ask for more and so on. That limits the address space of the program in some sense. That okay, this is all you get to work with. So this, at least the length of this thing is going to be static for the life of a program. And that basically depends on how big is your address space, how big is the like um, whether you have a 32-bit computer or you have a 64-bit computer, and that will basically tell that how many addresses a program can have, and that will limit its virtual memory. So this is the virtual memory of a program.
So,
Yeah.
Do you mean that uh, in the actual memory, the heap and stack might not be located together, or
Yes.
when they expand, they can be located somewhere else, some parts in that?
Definitely. That, in fact, that does happen, because when you just put a program like this, a process like this, now oops, if you just put a process like this here, and then now the stack, and even if suppose you implemented it, which like that, the way it's written there, that okay, you just gave it this much memory and then started doing that, but even then when that finishes, then you need the memory elsewhere. So this is so this is the OS part, that this is how the physical memory looks like, and the program will not be concerned with this. Program will always look at the memory like this, that it has a code, it has a heap, it has a stack, and there is some free memory in between. So I'm trying to emphasize this a bit, but this is very important, that the program's view of memory is not the same as the physical memory, and it might correspond very arbitrarily to how the things are mapped in the physical memory. In fact, yeah, whenever you run a program, and so in C, have you ever tried to uh, print an address? So you guys have done some data structures and some basic programming in C, right? So have you tried to print an address? That okay, this is where, yeah. So that address, where do you think So suppose you get some address, whatever, some 16-bit, 32-bit, whatever thing, some long string. Where do you think, what does that mean? Where does that point? That's an address here, or that's an address in the physical memory?
So the physical memory probably.
No. So that is the point. That whatever address a user program can see, print, let's say, is virtual address. So if time is there, after I do what I had to do, we can run a program and see that, okay, this actually corresponds to this view, that, okay, this is the stack at the bottom, this is the heap, and there's the code somewhere. We can find the location of all these three in the program. And I mean, you can try that on your own also to see, but it's always going to be that the stack is going to be at the highest address, the heap is going to be at very low address, and the code is going to be at 0 or something. And yeah,
Okay, so typically the stack and heap they have their own limits, right? It's not that usually stack is smaller than heap.
they can have, yes.
So in that sense, like it need not start from the bottom, right? I mean,
No, it will always start from the bottom. It grows up, right?
no, I mean anyway, stack and heap will have their own limits, so we can start the stack from a bit top, right? I mean, we can, but
I mean, you can, as I said, this is just a convenience. So if you have some alternative way of doing this, or then that can be done. Maybe if you want to just put the stack right after the code and limit it, like yeah, that can be done. That's what you meant, I guess.
yeah, not exactly, but yeah. So what I exactly meant was heap will have a fixed size when you run a program, and stack will have its own limit.
Heap does not have a fixed size. I
I
mean,
mean, the maximum limit is fixed, right? It cannot exceed some size.
the program itself cannot exceed certain size. So of course that would put limits on. But you're saying that okay, that limit might be the stacks limit might be much less than that.
Yeah. So
Okay.
we can place things accordingly, right? The starting of the stack.
Okay. So what is your suggestion, or what is your idea that how alternatively this could be done?
No, it's not a suggestion, and I'm just asking it. Like I'm just asking, uh, like we can push the stack a bit to the top.
So if you start the stack slightly above, and you are saying that now the stack will grow down. Is that what you're
Yeah.
suggesting?
Yeah.
Okay, yeah, that can be possibly done, maybe. But then, like, yeah, if you actually have, let's say, memory limitation of stack and heaps such that together they don't exceed the limit of the program, right? Then yes, this can be done. Then you just allocate the stack, the like whatever the maximum amount it has, and then you start it there, and then you grow it downwards. But then what are we achieving by that? So the same thing is true even here. That okay, so even if there is a limitation, you can mark that a hard way here, and that's where the heap can grow till. That's where the stack can grow till.
Okay, sir.
Right. Good. So yeah, the point I was trying to make was that whatever address we can print in a program, whatever address a user program can see, it's going to be a virtual address. So where the address actually maps in physical memory, this only the OS will know. So OS does all the dirty job of uh, translating these nice addresses to that a program can see to the physical memory. So always keep this in mind that whenever you are printing an address in a C program, it's a virtual address. We are looking at this view. We are not looking at the physical memory. We are looking at the abstraction of the address space. Okay.
So, sir, if we can know the idea behind the naming of these virtual addresses, then we can know or we can map it to physical memory, right?
if we know the idea behind.
The naming of these virtual addresses, then can we map it to the physical memory?
No,
Like
so the
where?
naming of the
Yes,
virtual address is always the location you mean. By naming, you mean the locations.
yes, yes, sir.
No, so the virtual address is always going to look like from 0 to whatever the maximum the address space can be, which is going to be the same for all the processes.
But I'm talking about this mapping from physical to virtual memory. There should be some formula or algorithm.
I mean, yes, there is a formula or algorithm, but that will be hidden from the process. That will be the job of the OS, and OS will hide it from the process, because otherwise, if the process knows this mechanism, then it can also want to access, some memory that it is not allowed to access. So
Okay.
the process is only given this view.
So as a creator, I can map.
Yeah, of course. If you're writing kernel code, if you're writing an OS, then yes.
Okay.
In fact, that will be discussed, that okay, how these things should be handled by an OS and so on. But for a process, a user process cannot see this.
Okay.
So it's a many to one mapping, right?
Of course.
Like, so it can't be invertible.
No, what? Sorry, no, not many to one. It's like um, it's how to say. So it's injective. So here, one physical address will be mapped only by, how to say. So there are many virtual addresses which are the same. So this is a multi-set. It's not really a set, so to say, on the left-hand side,
Okay. Yes.
because there are many values which have the same and they all map to different things. So this is suppose physical memory, and this is the virtual set. So in the virtual set now there are the same address space is shared by like every process. So there are going to be so many zeros as there are number of processes, right? And all those zeros are mapped to different locations in the physical memory. Does that answer the question? Or
Yes, sir.
okay, good. Okay. So so that is the question that Gijesh was asking, actually, that in a way that okay, how does the OS do this? Like, so how does this mapping, or so the question is like, how does the OS provide this abstraction? That is private, can grow to be large, or is large, let's say, and this for multiple processes, right? So the OS does not only provide one process this address space, it provides multiple processes for multiple running processes, but using only a single physical memory. So this is the basic question that we want to answer when we are trying to understand like virtualization of memory, or this particular abstraction that the OS provides. So yeah, so how does the OS provide this? Of course, like by virtualizing the memory. So what does it mean? Just like virtualizing the CPU, the running program would think thinks that it is loaded at address 0 and has a very large address space. As I said, depending on whether your operating system is 32-bit or 64-bit, it's going to be like 2 to the power 32 bytes or 2 to the power 64 bytes. If the byte is the lowest chunk of memory that you can address, right? Okay, good. So this is what the running program thinks, but in reality, what happens? The running program occupies much less memory than that. Utilize. Okay. And also not at 0, but at some arbitrary location. Okay. So, but then just so if there is a process A that wants to perform some load at some location, as Gijesh was asking that, okay, so there has to be some mechanism to do this, and so if A wants to perform a load, let's say, at some location, then it's responsibility of the OS to make sure that the load happens at the right place. Let's say like 10. And not at 10 exactly. Okay, good. And for this job, the OS will need some hardware support also. Okay, good. So now we'll look at some goals that the OS will have to keep in mind while virtualizing the memory. So, what are the properties that we would want from this implementation? So now we want to do this. At least the like framework is clear that okay, the OS will keep many addresses mm, in the many processes in the memory at the same time, but each process will think that it has all the memory to itself. It is loaded at address 0 and there is nothing else. It's just this process. And yeah, the OS will translate those addresses to the actual physical ones. Okay, so what are the goals? While virtualizing the memory. So the first one is going to be transparency. And like so this is different from like how we use transparency in our like day-to-day life or in like in terms of handling things by the government and so on. So currency in terms of governments or organization. So there what we want is like okay, everything should like we should know what is going on. But here it just means kind of the opposite. Organization. But here what we want that okay, what is the thing about something being transparent? That it's basically invisible. That the implementation of virtual memory is invisible to the program. Okay, so the program doesn't have to worry about basically. So this whole thing is hidden from the program. So the program is using the CPU, program is doing a lot of things, but in between there is this thing that is basically transparent. So that's what the transparency here means. That the program sees the CPU, program sees whatever, but there is this memory management thing going on, and the virtualization of memory that the program is like completely unaware about, and that's what the OS would want to achieve. Okay, so basically the program does not even know that I mean, of course, the programmers know, but the program does not care or worry about. So we can say that the program does not know or care about memory being virtualized. Okay. And like as I had said earlier, behaves as if it has all the physical memory. And the hard work is done by OS. Okay, so what is the second goal? Second is going to be efficiency. So What are the two main resources in a computing system? Yeah. What are the two main resources? What do we try to optimize all the time while performing
Time
it?
and space.
Speed and space.
Yeah, time and space, right? And yeah, different from time and space, which we have in physics. Yeah, so we want to minimize time and space. So the virtualization itself should not become too much of a space consuming or time consuming thing, because then, like, um, a process, how much time it should take, that time becomes dominated by how much this like overhead thing is taking. So that is not desirable. So the virtualization should not dominate, let's say, the space taken or the runtime of a process. So this is also, I mean, quite natural to ask for that. Okay, you are just, doing some administrative work, and your administrative work is taking, like, more time, more space than, what the process actually would have taken. So that is, of course, not very uh, good. And the third is going to be protection. So as we said earlier, that protection, the OS would want, like, not only for one process from other processes, but also protecting the OS from processes. Okay. So basically, what we want, that whenever a process performs anything memory related, let's say, it should not affect access or affect memory space of any other process or the OS. So in fact, this is a property that is achieved, and the property is called isolation. So what does isolation mean? Mean that it means that a process runs in, like, its own, like, cocoon, and it is not affected by others. It cannot affect others. So this shell, I don't mean the, like, OS shell. The shell means, like, a hard covering on shell, unaffected by other processes, and also cannot affect other processes. Okay, so why is this, like, important? Because isolation is, now we live in COVID times, and we all know that. Okay, so this is like, if one thing goes bad or one thing like goes wrong somewhere, then it should not affect like, something else or all the other things and so on. So that is why isolation is a good property. So it like, if one thing fails, still others can go on. So that is the main idea, that okay, one process fails, but that should not mean that okay, the OS crashes and so on, right? And in fact, some OSs, if you find examples, that they isolate parts of OS from each other. That one part of the OS should, like, if it fails, then it should not affect the other part and so on. So this is like, as much as you can isolate things, then like that makes even like debugging easy. That okay, what went wrong? Then you have one thing that has failed, and you can go there and find out that okay, what exactly has gone wrong there. So isolation does this. Okay, so this is like for the like introduction to the memories, the abstraction of memory, the address space. And now, just like we had some APIs for processes that, okay, how do we handle processes and how do we manage processes and so on. So similarly, we have some memory APIs also. So I'll just briefly discuss that. But I would urge you to just go through the chapter in the book. It's not very like long. It's simple enough, and uh, yeah, it discusses these two things that I'll like briefly discuss right now. So the question is like, how to allocate or manage memory. Okay, so as I told, there are two kinds of memory. One is the stack, one is the heap for a process, right? So how does the memory get allocated to stack? Does anyone know? Or okay, so let me rephrase the question. So what gets stored on the stack? We've talked about that, right?
So some variables which are local to a function.
Exactly. So yeah, so like suppose you have a function and you just declare an integer, let's say. So this will be stored on the stack. I mean, the memory, when the like program will come here, the compiler itself will assign a location on the stack for the variable x. So there is nothing like a user needs to do to uh, manage the memory of the stack. Okay. So and when we return from the function, then the compiler deallocates them. So this memory that is given to the stack, it is, as Arpit said, it is going to be just local for a function, but there are some things, or we would want something which might last longer, which are not very local to a function itself, right? So what if we want something to last longer? And that's where the heap comes in. Okay. So I'm going to write the line that is written in the book, and so we'll try to analyze that. That how do we allocate memory on the heap? So suppose we write something like this. Okay, so what does this achieve? So let's analyze this line. That what does this do? Can somebody tell that basic idea of what this line is doing?
So malloc allocates some space on heap. It's given an argument which is the size of int, which so it will allocate like those number of bytes in the heap, and it will return a pointer to that memory.
There is that's completely correct, but in this line there is just a little bit more going on.
The pointer is stored on the stack.
The pointer is stored on the stack. That's correct. Yeah. So here what we did, we first declare that okay, we are going to have an integer pointer. Okay. So then the compiler allocates memory. So compiler allocates memory for the pointer on stack. Okay. Now, when the program actually calls malloc, then the so this is so malloc, you should read the manual for this. That what exactly is its argument. So this is basically number of bytes that you want to allocate some something on the heap, and then malloc returns the address where it has allocated the memory, as Apit was saying. Okay. So that address, so yeah, so now when the program called malloc, it requests space on the heap. So malloc allocates that space. Size is defined by the argument. And returns the pointer to that location. Okay. So, and this pointer to location is then stored on this place. So this pointer is stored on the stack. Because we have declared an integer pointer there. Okay.
Sir, what was the point of allocating space on the heap?
I mean, you might want to use it for something. I mean, like you might want to use it for different functions. So, as I said, if you make just one, like, just declare a local variable, then when the function call will return, the like compiler will deallocate all the memory from the stack, which was assigned to that function, right? So, who, Shaurya, you asked? Who asked? Who asked the question?
Sir, I did. Like I got disconnected.
Ah, okay, okay. So, did you hear my answer? So,
Yes,
what?
sir. Sir, I
Yeah,
have to read more about malloc to understand more.
yeah, definitely you should. But like, yeah, your question was why do we need memory on heap? So, one, I think the let's say preliminary answer to that can be that whenever the like if you declare just a variable in a function, then whenever the like function call returns, then the memory will be deallocated. So if you want to use that that memory or that variable or something which by another function, then you would want to allocate it to the heap. Okay.
Yes.
Okay. Good. So this is so yeah, you should read more about malloc definitely. So that is going to be like a homework, and of course you'll need that in like for further assignments and so on also. And this is actually, of course, will be. I mean, if you were doing any data structure that is like dynamic, which would ask for memory, like linked list or anything like that, then that would require dynamic allocation of space. Then you need that function. And then for managing, there is also the free call. And so what it does is, so suppose you did this, the earlier line, malloc, let's say whatever, 8 times the size of integers. So you like stored, sorry, you allocated the space of 8 integers, like and stored the pointer in X. And now what you do is basically you just, now you're done with it, you don't need that space anymore, then you just call free X, and that will do the job of freeing that memory from the heap. So as you see that for free, no size is passed by the user. So then the the memory allocation library will have to maintain these things, that okay, uh, how much space is there for this pointer which has been allocated by malloc. Okay, but you should only, or you only call free for memory allocated on the heap. So only for user managed memory you called free, which has been allocated, which has been requested by the user and been allocated on the heap. Okay. So yeah, so these are the two basically very short. Like these are the two calls that will manage the memory. And another thing, as you see that I don't say that these are system calls. Okay, these are just like some how to say these are some procedures or which are available for a process, but these are not system calls in themselves. they might use system calls, or they would use system calls to ask the OS if the space is needed, like somewhere else, and so on. But these are not system calls by themselves. So if you read the chapter, you'll find the system calls like brk pick and so on, which are there. But it does not go into detail. But just to keep in mind that these are not system calls. These are just procedures which are available for a user to use for when it wants to get space allocated. And these run on top of system calls. So these might request some system calls to allocate the memory. Okay. And then the chapter lists like some common errors while using malloc and free, and like some of them were like forgetting to allocate memory before using some address. So for some routines, especially like, you require to give the, specifically you need to have that much memory there. So suppose you have a character pointer and then you just want to, copy some things there, and you have not really allocated memory to that as a string there. So you don't have that many characters memory there. You just have a character pointer, and then you want to do that, and then the procedure will not work because it would require you to have allocated memory there at that place. So you should always allocate memory when you use such procedures. Also, you should not generally forget to free memory. So you should make a practice that whenever you do malloc, you free that memory before you exit the program. So it does not matter for like small C programs which like run and exit, because when it exits, anyway, the OS will take care of it will just uh, take back all the memory, not just the heap memory, but the stack memory, the code memory, everything it will take back. But if you are running programs which are going to be lasting, and I mean, if you want to be a programmer, if you want to write code, then you want to write system code sometimes, like kernel code, or some database code which is always running, and then you don't want to forget to free memory, because this is, if you don't do that, then this results in something called memory leak. And if that keeps growing, it can crash the system. And then there are some other issues that the book mentions, which is like freeing memory before you're done with it. So suppose you are going to access something, but before that you have freed the memory. So that's called a dangling pointer. Then suppose you free some memory repeatedly. So this is undefined behavior. And suppose you call free incorrectly. Suppose you call that for some local variable or something like that. So that is also undefined. So these are the common errors that the book lists that you should avoid. And I mean, the book says that this is these were the most common ones in so the people who have written the book are much more experienced than me. So maybe you should listen to them, that you should avoid those errors. So that's it for today. And yeah, any questions or any comments, anything? So next time we'll talk about these uh, address translation stuff and so on. Okay, no questions? Cool. Thank you for coming, and let's meet on Thursday. Same time, 9:30. Thank you.